This is the second lecture on atomic structure. So I'd like to explain why we are starting with the atomic structure. In order to do so, let's look at the different length scales on which we can understand materials. The largest length scale is the macrostructure, and this relates to features that can be seen in a material using the eye, that are visible by the eye. Let's look at some examples here. These are 3 jet turbine blades that have been manufactured in different ways. These circles here, these insets, show the microstructure superimposed upon each turbine blade. We can visually see the surface of these 3 blades are different, and that is the macrostructure. Let's try to explain why the visual appearance is different. To do so, we will need to understand the microstructure. The microstructure is of the order of tens to a few hundred micrometers. These are the length scales that are visible using an optical microscope. In the inset microstructures, we can see that the grainy looking turbine blade has a polycrystalline structure, microstructure, meaning it is composed of small, randomly orientated crystals. The turbine blade that looks as though it has stripes running up and down has a microstructure that shows that it has columnar grains or columnar crystals within it. That's because this turbine blade was directionally solidified, a processing technique. On the right, we see that the microstructure of the single crystal turbine blade is featureless because there are no grain boundaries. The entire turbine blade is a single crystal. So the next level of detail we can go down to is the atomic organization. This would be on the scale of nanometers. Here we are on the scale of atomic organization. We can see how the individual, or we are looking at how the individual atoms are positioned. In this diagram here, we show the unit cell for a face-centered cubic structure, showing how the atoms are arranged in a regular lattice. This would be the atomic arrangement within each of the crystals shown in the microstructure. Within each atom, we can look at the atomic structure or the subatomic structure. And here we have a simplified model of the atom showing a nucleus surrounded by orbiting electrons. From the previous example, we can see the interplay between the processing that gives the turbine blades their different microstructure to the properties of the blades and finally to their performance. Below is another example of this. Here we see 3 pucks of identical composition. All 3 of them are made out of aluminum oxide. On the left, this material is single crystal and is transparent and clear. The middle sample is polycrystalline aluminum oxide, and we can see that the grain boundaries diffuse the light passing through it. The sample on the right has been formed through sintering. This involves taking grains of aluminum oxide, pressing them together, and then firing the result in the furnace to cause the grains to bond with each other. we can see that the sintered material is not transparent at all. Once again, we can see how the processing of the material gives rise to a structure, which in turn gives rise to the properties we see here, in particular the optical properties illustrated in the picture, which then relates to the performance of the material for a particular application. We will now discuss the structure of the atom in a very simple way. Richard Feynman, a famous Nobel Prize-winning physicist, once said that if all knowledge were destroyed and he could only pick one thing to pass on to the next generation, he would pick that all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. This shows the simplified model of the atom. At the center of the atom, we have a very small, positively charged nucleus. Surrounding the nucleus are electrons, which are in well-defined orbits. This is a very simplified picture, and the electrons do not actually move around as particles in such orbits. But this picture is a very useful way to introduce atomic structure. Let's first look at the nucleus. Inside the nucleus we have nucleons, and the nucleons inside the nucleus are protons and neutrons. The protons are shown in red in this diagram of a carbon-12 nucleus, and the neutrons are shown in white. The mass of an atom is almost entirely due to the mass of the nucleus. The mass of the electrons is negligible. For each Avogadro number of protons or neutrons, what I mean to say is that each Avogadro number, which is 6 times 10 to the 23, if we have 6 times 10 to the 23 protons, the mass of them will be 1 gram. Similarly, 6 times 10 to the 23 neutrons would also weigh 1 gram. Counting up the total number of nucleons within the nucleus gives us what is known as the atomic mass of the atom, and this is known as the mass number, given the symbol A. Here we see 2 isotopes of carbon. Isotopes arise when the number of protons in the nucleus stays the same, but the number of neutrons changes. So why are these 2 nuclei still called carbon? Well, that's because the chemical characteristics of an atom are dependent upon the orbits of the electrons surrounding the nucleus. For the atom to be neutral, the number of negative electrons must balance exactly the number of protons in the nucleus. In both the nuclei shown, there are 6 protons, and hence both of these nuclei will be surrounded by 6 electrons in identical orbits, and hence will be chemically identical. The heavier isotopes tend to be radioactive, and this is one way to identify them. Another way is to use a mass spectrometer. As we can see, the number of protons in the nucleus is very important characteristic of the nucleus, and that number is called the atomic number, designated by the letter Z. The atomic number gives us the number of protons, which in turn is equal to the number of electrons in the, I shouldn't say outer shell here, this should say the number of electrons surrounding the nucleus. As I said before, this simplified picture of a nucleus with electrons as well-defined particles moving in orbits around the nucleus is a very simplified model, which breaks down and doesn't explain all phenomena. In order to come up with a more accurate theory, physicists realized that objects behave differently on a small scale than they do on a large scale. The laws that govern particles on a small scale are called quantum mechanics. And on a small scale, objects behave like waves and are described by a wave function, shown here by the symbol psi. The wave function appears in this famous equation called Schrödinger's equation. By solving Schrödinger's equation, we can solve for the wave function. The wave function can tell us the probability of finding that particle at a particular position. The shape of the wave function is dependent upon the potential function. And if we solve for the wave function of electrons which surround a nucleus, we can solve for the shape and characteristics of the electron orbits. When this is done, Schrödinger's application of Schrödinger's equation confirms Bohr's model of the atom, which is that the electrons can only exist in well-defined orbits with well-defined energy levels. The energy levels cannot have any value, but only certain discrete values. This is called quantization. Here we see a visualization of the wave functions, the three-dimensional wave functions for different orbitals that the electrons may inhabit. This is a spherically symmetric s orbital. Here we see a p orbital in different orientations, and here we see the shape of a d orbital, again with different orientations. The different orbitals have different energy levels. So, for instance, s, p, and d orbitals have different energy levels. Each quantum state is described by 4 quantum numbers. Each electron must have a unique set of quantum numbers, as 2 electrons may not occupy the same quantum state within the atom. This is known as the Pauli exclusion principle. Let's have a look at these 4 quantum numbers. The first quantum number is called the principal quantum number, or the shell number. And this is a number that is an integer with a starting value of 1. Within each shell there is a subshell. The subshell is characterized by the azimuthal quantum number L. L can go from 0 to n-1. The subshell can contain a number of orbitals. All electrons in a subshell have the same energy level in the, I should say, in the absence of an applied magnetic field. The orbitals within the subshell may be calculated by looking at the possible values of the magnetic quantum number m, which can vary from -L through 0 to +L, and the spin quantum number of each electron, which may be +12 or -12. The ground state of a neutral atom is that in which all the electrons have the lowest energy states possible. In order to calculate the ground states, we will apply the Pauli exclusion principle in combination with the possible orbital quantum numbers. In this table, I have delineated the possible orbitals for different shells. Let's start with the quantum shell number n equals 1. From the previous slide, we see that for an n equals 1 shell number, the possible values for the azimuthal quantum number will be from 0 to 0, or in other words, it can only be 0. Shown here, 0. Oh, sorry, shown over here, 0. This is historically called the S shell. So we have the S subshell. So 1s forms a subshell. The 1s subshell can have a number of orbitals. Let's find out how many there are. Well, the magnetic quantum number can vary between m equals -L through to 0 to +L. But in the case where n equals 1, the L can only be 0, and hence the magnetic quantum number can only be 0. However, the spin quantum number can still be +12 or -12. This tells us that in the first shell, we can only accommodate 2 electrons. The orbital quantum numbers for these states are given by n equals 1, L equals 0, m equals 0, and the spin quantum number can have a value of +12 or -12. Let's apply the same thinking to the second shell. In the second shell, the azimuthal quantum number can vary between 0 to 1. For the S subshell, once again, the magnetic quantum number cannot vary. It can only be 0. And accounting for the 2 different spin levels, the 2s subshell can accommodate 2 electrons. In the P subshell, the magnetic quantum number can go from -1, 0 to 1. And each one of those subshells can accommodate 2 electrons. Hence, the total, I should have said each one of those orbitals can accommodate 2 electrons. So in total, we have 6 possible orbitals under the 2p subshell. If we add up the total number of electrons that can be accommodated in the second shell, we get 8. And we can carry on in this manner. To determine the ground state now, we need to place the available electrons in the lowest energy levels. Generally speaking, the lower the quantum number, the lower the energy, and the lower the azimuthal quantum number, the lower the energy. However, there are some deviations from this pattern, which are shown by this diagram. Initially, the pattern is followed. 1s is the lowest, 2s is next, then 2p, then 3s, and then 3p. But here we see the pattern is broken when we find that the 4s subshell has a lower energy than the 3d. This means that the 4s subshell will fill up before the 3d when we are determining the ground state of the electron. These variations are nicely indicated using what is known as the Aufbau diagram. Just typing in Aufbau. The Aufbau diagram has been applied to determining the ground state of the iron atom. Iron has 26 electrons. Let's see how these are accommodated by the different shells and subshells. The lowest energy shell is the 1s, which can accommodate 2 electrons. The next lowest is 2s, which can accommodate another 2. Then, following the diagram, we have the 2p. So far we have accommodated 10 electrons. We keep going, 3s, 3p, and 4s. At this point we have filled, up to this point we have completely filled the suborbitals, and we have accommodated 20 electrons. However, the d shell, which we showed in this diagram, can accommodate 10 electrons. However, we only need to accommodate a further 6. This results in an outer suborbital that is partially filled, subshell that is partially filled. And this has important consequences for the manner in which iron will form bonds with other elements. It is also possible for the subshells S, P and D to mix, forming hybrid orbitals. These are extremely important in organic chemistry and explain the wide variety of compounds that carbon can form. We will be looking at hybridization when we discuss the topic of polymers later on in this course. But if you are interested in learning about hybridization, I urge you to look at a very nice animation which is at the link shown in your notes, or rather in the PDF files of this presentation I've posted on etudes. When we looked at iron, we realized that the outer subshell was partially filled, and we stated that this would have important consequences for the chemical behavior of the element. This is generally the case, and the number of electrons in the outer shell of an atom that are involved in bonding with other elements is called the valence number. In this case, in sodium, we can see that the valence number is dictated by the number of electrons in the outer shell, which is the n equals 3 shell, which contains 1 electron. Hence the valence number for sodium is 1. In the periodic table, elements are arranged in columns according to their valence number. Here we see sodium under 1. This arrangement allows us to quickly see the manner in which materials will combine with one another. Here we have the group 1 elements with 1 electron, with 1 valence electron, the group 2 with 2 valence electrons. In these materials, called the transition metals, the number of electrons in the outer shell, or the valence number, can change, and hence the name transition metal. These materials here, in the 3rd, 4th and 5th columns, or groups rather, are very interesting because they exhibit the hybridization of the bonds and can form complicated and interesting, or can form complex molecules. The group 7 elements are called the halogens, and they are highly reactive. The group 0 have 0 valence electrons. That is because they have their outer shells are completely filled, and they already have a very stable electronic structure, and hence do not participate in bonding, and it is very difficult to further decrease the energy levels of these atoms. Electronegativity is the tendency of an atom to accept electrons. Atoms tend to form bonds when the resulting molecule or compound will lower the energy of the overall system. This happens when electrons are shared between the atoms. In an extreme case, an electron can be lost from one atom, or can be considered as being lost from one atom and gained by the other. A simple way to look at this is to say that the atom is stabilized if the resulting outer shell is full. We can see here that with sodium this can be accomplished if the single electron in the number 3 shell is removed. I should have drawn this arrow going over here to explain how adding an electron to the 2p subshell completes the outer number 2 shell for fluorine, hence lowering its energy. So this concept of electronegativity is a measure of the tendency of an element to accept rather than donate electrons. Fluorine is the most electronegative element. In this diagram, the electronegativity of each element is shown on a plot, on the three-dimensional plot. The height of each column is proportional to the electronegativity of each element. We see that fluorine, by the convention used to measure electronegativity, has the highest electronegativity at a level of 4. All the other elements are compared to fluorine. The electronegativities may be calculated different ways, and what's shown here is using a method determined by Pauling, and is calculated using the bond energies that these elements will have with fluorine. We can see that on this side, on the group 1 and 2, we have low electronegativity. We can say that these materials are electropositive and have a tendency to form positive ions. We can predict that mixing an electropositive material with an electronegative material will result in an ionic loss of the electron from a positive material, from the electropositive material to the electronegative, hence forming ions. We've introduced the concept that sharing electrons can reduce the energy of a system of atoms and hence result in attraction of those atoms, or in other words, bonding. There are 3 types of primary or chemical bonds: the ionic, the covalent, and the metallic. Ionic bonds form in compounds between elements that have very different electronegativities, meaning that the electrons, rather being shared, are captured by the electronegative element in the compound. Shown here is a schematic representation of sodium chloride. We can see that there is, in order for this crystal or this arrangement to be neutral, the number of chlorine atoms, which have a charge of -1, must equal the number of sodium atoms, which have a charge of +1. This is called a stoichiometric ratio. Due to the difference in electronegativities, the atoms are in an ionized state. And due to Coulombic attraction of oppositely charged ions, bonding occurs. In ionic solids, the movement of one plane of the crystal relative to the other is very difficult, as it will require charges with like charges, or like charges being moved close together. Electrostatic forces are extremely strong, and this results in ionic solids being very rigid and hard and brittle, because there is no mechanism for slipping and deformation to occur. Let's look at now covalent bonds. In the ionic bonds, the electron is not regarded as being shared, but as being lost by one element and given to the other. In covalent bonds, the electrons are shared in molecular orbits, and this results in a lowering of the energy of the system and hence bonding. Here we see carbon bonding with 4 hydrogen atoms. To explain this fully, we would have to understand how the S and P shells, or subshells, in the outer shell of carbon form hybridized orbitals. But a very simple way of explaining this is to say that the sharing of electrons creates a filled second shell for carbon, hence lowering its energy level, and similarly, sharing of electrons creates a filled outer shell in hydrogen, hence lowering its energy. The characteristics of covalent bonds is that they are highly directional, in the sense that there must be a fixed geometry between each of these bonds. The compound shown, methane, actually has a tetrahedral structure. This fixing of the directional relationship means that covalently bonded compounds are very rigid. Diamond is covalently bonded and is the hardest material known. As we can see, the electrons are localized, much like in ionic solids. This means that they are not free to move and cannot participate in conduction. Covalent and ionic solids do not conduct electricity. Although with ions, it is possible for the ions themselves to be carriers and move around defects in the lattice. But that is not possible with covalent materials, and so covalent materials are good insulators. We can see here how an understanding of the atomic structure and the bonding, and the type of bonding that atoms engage in, can be used to predict or explain the physical properties of the material. In the metallic bond, we have what can be regarded as a large-scale covalent bond, in the sense that the sharing of electrons is lowering the energy of the system of atoms. In the metallic bond, we have atoms, each of which have lost some of their valence electrons to form a sea of shared valence electrons, which bonds the structure together. This results in bonds that are not directional and allow one plane to slide with respect to the other. This explains why metals are ductile. The shared electrons are delocalized and are free to move and participate in thermal and electrical conduction. Once again, by understanding the nature of bonding in the material, we can explain physical properties. A type of secondary bonding is called van der Waals bonding. This occurs when the molecules are polarized in terms of their charge. This means that the center of the positive and negative charges in the molecule are displaced with respect to one another. In other words, the molecule seems to have a positive end or a negative end. This can occur through random fluctuations, or can be a result of the shape of the molecule itself. For instance, in hydrogen fluoride, we have a strongly polar molecule. In van der Waals forces between strongly polar molecules is called hydrogen bonding. Hydrogen bonding is responsible for the formation of ice. In what we've discussed so far, we discussed the primary bonding types as being distinct and separate. In most materials, the bonding is a mixture of two or more of the principal types. Metals can have a mixture of metallic and covalent bonding. The greater degree of covalent bonding results in a greater hardness of the metallic material. In ceramics and semiconductor materials, the bonding can be a mixture of covalent and ionic types. As the electronegativity of the atoms increases, the bonding becomes more ionic in nature, and the covalent fraction of the bond can be calculated using this formula, where delta E is the difference in the Pauling electronegativity between the elements. Binding energy is the energy required to break a bond between the atoms. The larger the energy required, the stronger the bond can be said to be. Van der Waals forces are extremely weak, so weak that mere small thermal agitation can break them. Metallic bonds are the next strongest, and here we can explain their moderate performance under high temperatures. Covalent and ionic materials have the highest bonding energies and require high temperatures to be disrupted. And this explains the strong bonding, explains the high temperature resistance of such covalent and ionic materials. Although it should be remembered that not all covalent materials will have a high temperature resistance. So that's all for the second part of the course. Thank you.